Okay, let's continue electrical systems. The second element that we will be looking is called the resistor. I'm sure you all know this since high school. We show it in a schematic with this symbol, and for our across and flow variables, we have the relative variables VR, and sometimes we show it IR in a graph. This is IR, this is VR minus there is a I talk about the resistor and the inductor also. I talked about the inductor. I didn't recall this. Okay, let's skip this then, therefore, since I mentioned to you. And how about the op-amp? Op-amp, so we'll talk about the ideal op-amp then. You had probably seen it in electronic courses or other courses. This is the schematic view. Now I have a little bit more complex element. It has 1, 2, 3, 4 terminals, which is called two-port. For 2 ports, this is a block diagram representation, and if I had to show with the graph, I was supposed to show 2 branches here for actually the op-amp has 3 ports. This is minus, plus, reference, output, reference. So if this is negative, positive output, and P output, and this is our ground representation would be. So it becomes a little bit more hairy to show it in terms of graph or block diagram. Let's have a look at this characteristic equation. Since it is more than one port, we have to have at least 3 equations for this guy. Ideal op-amp will have virtual grounding inputs, which means that Vn is always equal to Vp. In terms of the voltage, it looks like short circuit. It is like the same. Whatever voltage you apply at P node, it will appear in the N node. Okay, and also it's like when we look at the current that go IN, IP, you will see that IN is equal to IP is equal to 0, and it looks like an open circuit input terminal. It's a weird, confused component. It doesn't know it's a short circuit or open circuit. At some aspect, it is called connected. It's some short circuited. It's when you look at from the current, it acts like an open circuit element. One of the reasons we have this sharp, abrupt definition of the characteristic in the characteristic equation. This is an ideal element. It has Zi. The input impedance is infinity. Gain, differential gain, is also considered to be infinity, and output impedance is equal to 0. This is a ideal amplifier characteristics. These are And this is why it's called operational amplifier, because of that. In an ideal amplifier, not having a loading effect and driving any circuit, these are the properties that you would like to see. Plus, you have a good gain, a infinity. It's also another good positive effect that we have. When we try to look at the op-amp circuits, we are gonna start with the most basic one, R1, R2. I'm gonna connect VI here, input voltage and output voltage. And when we look at this as a system, from VI input, V0 output, we'll try to find out a transfer function, a model for this system. So in order for me to do that, I need to find out the input-output relation between V0 and VI in S domain as a polynomial, as a transfer function, if I can find. We are going to make a note here. When we try to analyze any op-amp circuit, always start with feedback node equation. So from output to input, we have this feedback in the op-amp circuit. I'm going to write the node equation for this node. Sum of all the elements attached to this guy admittances, 1 over R1 plus 1 over R2 times V negative terminal, minus between this node and every other node, if there is any connection, we write this down as 1 over R1 VI minus 1 over R2 V0 equals, let me write non-ideal characteristics in here. If I have I0 here minus IN equals 0. There is no current source attached to this node. From the characteristic equation of the op-amp, Vn is equal to Vp. Vp is connected to ground, so Vn is equal to 0. And In is equal to Ip is equal to 0. In is equal to 0. This is actually V0 is equal to minus R2 over R1 Vi. This is the transfer function. So my G of S is a static relation, R2 over R1. There is no S term on it. So this is the transfer function or a model of this system. It's called inverting amplifier. By making R2 greater than R1, we get the amplification of the input at the output. And with the minus sign, we are changing the polarity of the input signal. When it is positive, it will become negative, vice versa. This is one of the most common use of op-amp amplifiers circuitry. Probably most of you have seen it. If we have an inverting amplifier, we should have also non-inverting amplifier. I'm going to connect VI in here, R1, R2, V0. Another note I'm going to write here is you are seeing the feedback port is always negative input terminal for amplifier circuits. If you are going to be using op-amp as a linear amplifier, you must always get this output to input feedback from the negative terminal. With the ideal op-amp equation, if I make this feedback from output to the positive terminal, you will get the same answers because it's virtually grounded, virtually the same note that we are going to have here. However, that op-amp would not work as a linear amplifier. It will saturate and it will become a non-linear component. So don't do that. You always, when we are talking about the amplifiers, always take the feedback from the output to the negative terminal. Now, our previous page note was saying us we need to get the feedback from the output to the input, and we need to write the note equation always from the negative terminal. If I do that, sum of all the admittances attached to node 1, same as what we have seen it in the previous example, Vn minus 1 over R2 V0 equals 0. And from the characteristic equation of op-amp, Vn is equal to Vp, which is equal to Vi. If I substitute it in here, I would get V0 is equal to 1 plus R2 over R1 times Vi. As you see here, the input voltage is amplified by 1 plus R2 over R1 ratio and sent to the output with no change in sign, no polarity change. So it is we get this non-inverting amplifier. Let's look at we have V0 is equal to Vi, G of S is equal to 1. So this circuit is called buffer. It takes the op-amp characteristic of having infinite input impedance, which means that no zero is going to be sourced from the input connection, and it's going to be buffering the signal that you have here at the Vi, and then we will get the same signal at the output without sourcing any signal from it. Typically, when we have sensors, we are going to have the important information of sensors. This is what we want to show, and the internal impedance of the sensor is going to be represented by Rs. This is going to be my Vi signal. If I connect this to any load, RL, so, and if we try to look at the V0, which is equal to Vi, and it's going to be equal, this is the resistor divider. We will have RL over Rs plus RL Vs. This is the signal I wanted to send to the output. However, when we look at the signal at the output in terms of Vs, we will see it's going to be divided by RL and Rs. If input impedance of the sensor is a lot larger than RL, V0 is going to be approximately equal to 0. You are going to be losing most of your signal because Rs is going to dominate here, and you are going to see, even though there is an information here, that information is going to disappear if you don't use the buffer, if you just use the your system, try to get this information and process it. So this is not a good scenario here. To avoid that, what we do, I get this, the loading effect eliminated by this buffer circuitry. So we know that V0 is equal to V positive, V plus, and V plus is equal to Vs. Why? Here the current that goes through op-amp is equal to 0. So the resistor voltage drop across this resistor 0 times Rs is 0 volt. Therefore, whatever the voltage you have here is going to be same node is in here. Same node voltage in the V plus is equal to Vs. And then, as you see here, no load in effect is eliminated. All the instrumentation amplifiers have this buffer circuitry at their inputs. This is important because of that. Another key op-amp circuit is we have V1, V2, R1, R2, Vn, Rn, and let's put the feedback resistor Rf. Okay, and this is V0. What we said that for ideal op-amp circuit, when we try to analyze the system or try to get a model for this kind of electrical circuit, let's ground the positive terminal. All we need to start with feedback node equation. Here I have this node connected at 0. So I'm going to get 0 times sum of all the all elements admittances attached to this node is going to be 0. So 1 over R1 plus 1 over Rn plus 1 over Rf times 0. So I didn't have to write this actually. Minus between this node and every other node, I'm going to write elements admittances 1 over R1 V1 plus 1 over R2 V2 plus 1 over Rn Vn plus 1 over Rf V0 equals 0. So from here, I have V0 is equal to minus Rf over R1 V1 plus Rf over R2 V2 plus Rf over Rn Vn. So what we have, we are summing all the inputs V1 through Vn and then weighting them, scaling them by independent scale factor Rf over Ri. So this is called the summing amplifier. This is also a very important circuit and we love to use it in many applications in practice. And let's look at this circuit. Minus plus VI R NRC circuit V0. Again, I'm going to be writing node equation for this node, and this node is connected at 0. I'm not going to write that this time. Oh, let's do it one more time. Times 0. This is gone. Minus 1 over R VI minus SC V0 equals 0. From here, V0 is going to be equal to minus 1 over RC times S VI. 1 over S is going to give me the integral effect, and the scale by 1 over RC with the negative sign is changing the polarity. So this is called the integrator circuit. If I flip the place of R and C, we would get minus SC times VI minus 1 over R V0 equals 0. the node equation is going to give me this term, and from here I will have V0 is equal to minus RC times S times VI. So S times VI is going to give me the derivative effect. So this is the derivative taking circuit. If you take the derivative of a signal that has high frequency noise in them, so the derivative of the high frequency term in a short amount of time, you are going to see changes, relatively high changes. Therefore, you are going to amplify the noise. So we don't like this kind of circuit to be used in noisy signals. The signal noise ratio is going to be incremented drastically. So this is not a very good circuit to be used. You have to use it in caution. So if I make changes and get this my integrator circuit with a coupling R1, R2, and C circuitry. And since the virtual grounding at this node is valid, sum of all the admittances times 0 is going to be 0. So what I'm going to be doing, writing the other term, minus 1 over R1 times VI minus 1 over R2 plus SC times V0 equals 0. This is the node equation for an terminal. So from here, if I do the V0 over VI, let's divide both term to C. So R2 times C, R1 times C, C over C is going to give me 1. So I will have S plus 1 over RC minus, this is R2C, minus 1 over R1C. So this is the first order transfer function, G of S. First order transfer functions. If, for example, if I have G of S is equal to minus 5S plus 10, and if I wanted to create an electrical circuit that will give the same dynamic behavior, I would change it to analogous electrical system by this R1, R2, and C circuitry with 1 over R1C is set to be equal to 5, and 1 over R2C is set to be equal to 10. If I can find R1, R2, and C, 3 variables, to make sure that 2 equations are satisfied, I will have the same dynamical effect from this system, whatever the transfer function of G of S is coming from. This can be a nuclear energy system behavior. Instead of working with the nuclear energy central, you can work in the lab with the op-amp and a couple of RC to get the same effect of dynamic analysis of the system. So these analog circuits have been used, especially before the digital computers, as the analog computation. They are actually sometimes called analog computers. They used to be called and used a lot before. So how can we find 3 parameters to satisfy these equations? So we can say let C is equal to be, let's say 10 microfarad, a typical value that are designed to be used by the practical op-amps, and then apply this into equation. So R1 is equal to 10 to the power of 5 over 5, which is equal to 20 kilo ohm, and R2 will be equal to 10 to the power 5 over 10, which is equal to 10K. So if I put here R2 equal 10K, R1 is equal to 20K, and C is equal to 10 microfarad, the VI and V0 relation will give me the same dynamic behavior of this nuclear energy plant systems dynamic model. Okay, and I'm going to be studying another second order composite op-amp circuit. This is from Franklin and Powell's feedback control book. This circuit that I'm going to be plotting here right now. So we have VI R grounded, and I have here SC, and I will have here R1. This is going to give me V1. Then we run this through an integrator. We put the same R value and same C value here. And we have here a V2, R minus, and inverting amplifier. Same R value is used to get V0. Then from this V0, we take another signal, send it to the input, a negative terminal of the first op-amp circuitry. I have V0. Again, if you look at V0 is equal to minus VT. This is the inverting amplifier we have seen it before. And V2 from this node to this node was equal to minus 1 over RC over S. This is the integral circuitry times V1. We had seen this before. To make my life simple, I'm going to set R times C is equal to 1 as a constraint. So let R to be 10 to the power of 5 ohm and C to the 10 to the power of minus 5 farad. Okay, 10 microfarad and 100 kilo ohm resistors are used for R and C values to get that RC equals 1 equality. So I'm going to get minus 1 over S times V1 in here. After having these two equations, all I need to do here is write this negative terminal. So let me substitute here V0 is equal to minus V2, which is equal to minus 1 over S V1 after this substitution, or V1 is equal to S times V0, okay, into this equation. Let's write the node equation for this guy. I have sum of all the elements admittances times 0, which is equal to 0. Node equation for n minus 1 over R times VI. Then minus 1 over R1 plus SC times V1. V1 was equal to S times V0 minus 1 over R2 times V0 equals 0. So I made it very simple by making direct substitution to get this these equations. All right, let's do this calculations. V0 is equal to, I have here multiplicity by s. This is the s square, the most highest polynomial term. I'm gonna make the coefficient of this s square term to be equal to 1 by dividing it c, r1c, rc, r2c. Okay, and 0 over c is equal to 0. If I do that, what I'm going to get, s square plus 1 over r1cs plus 1 over r2c here, and 1 over rc was set to be equal to 0. I'm going to get minus 1 times vi. So I get this second order system with the denominator of defined by R1 and R2 coefficient. Since C is already fixed, therefore I have two parameters to assign any denominator of the second order system transfer function. But the numerator part has equal to minus 1. For me, to make this system more general, I need to get, for example, g of s is equal to b1s plus b0 over s squared plus a1s plus a0 most generic second order strictly proper system. Okay, transfer function will be some real coefficient of a0, a1, b0, b1 needs to be equated. I know by selecting R1 and R2 in this circuitry, I can emulate any transfer function's denominator. But for the numerator part, I'm kind of not there. I have constant in here, but not S term. When we look at the V1, V2, and V0, can we get any term will have S at the numerator part? We look at the V1 term is equal to S times V0. So S times V0, V1 is going to be equal to minus S over S squared plus 1 over R1CS plus 1 over R2C times VI. So by summing V0 and V1, I can get this B1, B0 coefficient properly. So if we get a new signal instead of V0, let's call it Y of S is equal to, I'm going to get minus B1, V1 plus B0, V0. I'm going to get this transfer function above as Y over Vi can be obtained. All I need to do here is apply this to a summing amplifier with the coefficient of B1 and B0 is set to be a gain factor. So not to lose the, not to plot this entire picture in here, I'm going to erase this part. Just plot below this circuit. So what I just said, that if I take this signal, and if I take this signal and apply this to a summing amplifier, let's go this way. And this is to be the output, and I have here our A, RB, and RF resistor is set in a way that I'm gonna get any generic B1 and B0 coefficient effect. The Y will be equal to minus RF over RA V1 plus RF over RB V0. This is the summing amplifier input-output relation that we have driven before. So if you can see it here, we can say that B1 is equal to RF over RA and B0 is equal to RF over RB. This is how we can obtain a generic transfer function that are given to us. Let's just illustrate this in a numeric example, and then again, I don't want to plug this crowded circuitry. I'm going to erase this guy in here and then give you some numeric example. Let's say that we have an in aircraft longitudinal dynamics or something that is very heavy and modeled as a second order transfer function. G of s is equal to 5s plus 8 s squared plus 10s plus 20. This is the transfer function of a very expensive system to put in the lab for analysis. What I'm going to be doing, I'm going to get this expensive system dynamic behavior in the lab represented by this composite op-amp circuitry. I need to set the parameters for R and C values. We said that R was always set to equal to 100K and C is set to be equal to 10 microfarad. You can change, you can set any values as long as R times C is equal to 1, it's okay. And once I have defined these R and C values, the remaining RA, RB, RF, and R1 and R2 needs to be determined to meet these 5 coefficients. So the first thing that I have here saying that the denominator have 1 over R1C is equal to 10 and 1 over R2C is equal to 20. These are the denominator requirement that I have in my transfer function needs to be satisfied. These are 2 equations will give me 2 unknowns R1 and R2. Then I have a question. Last minute left. Okay, thank you. Then the other remaining 2 equations is going to be obtained by RF over, I have here RA, that is the coefficient for S term, which is equal to 5, and RF over RB is equal to 8. If I have these 2 equations satisfied for RF is equal to 100K, and then or I'm going to make it something more interesting. If I have 5 and I have 8, I need to get something that can be divided by 5 and 8. 5 times 8 is 40. If I get the multiple of 40, 400K, then